Hi, welcome back. We're continuing our tutorial 12 about how to use Mathematica to do 3D printing. And now we're going to talk about creating some meshes and modifying the meshes. So one thing that might be nice and that's fun to do is to create a mesh that you could then modify directly from images that you have brought in from outside. So here was an image that I found on Google image search. I made sure that it was only black and white and didn't have any gray pixels. And so you can just drag and drop it into Mathematica, and you can use image mesh to take this and create a region based on your image. I've used color negate here so that our flower would be the region instead of the non-flower. It's taking the black and white image and making it white and black. All right, you can also use this to discretize words. So you take a word and whatever is your favorite font, and you can discretize it. And here is this region. Now you can do various things in Mathematica to incorporate this into your project if you're interested. All right, so let's talk about some of the different modifications that you can do to your meshes. It's very useful to be able to access some information from your mesh. To do that, you use mesh coordinates, and that will give you, oh, I have to define ball. Where did ball go? Let me take ball is equal to boundary, or just discretize region ball. All right, there's our ball. Let's take the coordinates of the ball, and what are the first 10 of them? Here are the first 10 coordinates of the vertices that make up the ball. And actually, I think I want to do a boundary discretize. All right, so now each of these coordinates are points that are on the surface of the ball. And if we were to graph them, then here are all the points. So if we're plotting them, here are all the points of the coordinates on the ball. If you want to access the line segments and the faces, then you can use mesh primitives. So here we're accessing the elements, the parts of the mesh that are dimension 1, which are the line segments. So here we have the explicit coordinates of the initial point, the end point of each line segment. And if we show them in 3 dimensions, here's what our edges look like. So this is the wireframe of our mesh. All right, and then what we can do is we can also ask for what the 2-dimensional parts of our ball are, and those are these polygons. Here are 10 of them. These are the polygons. And if we then use Graphics 3D on all of these polygons, then you get to see them all. Let's take maybe 100 of them and see what 100 look like. Right, so this is first. And if we do Graphics 3D of the first 100, here are the first 100 triangles that make up the surface of the ball. All right, so some other useful information that you can take out of, that you can get out of a mesh include the size of the region and the center of the region. So this is one of my favorite polyhedra. It's called the snub cube. You can access directly this mesh from polyhedron data by typing in the polyhedron you want and putting as the second input mesh region. So what we might want to know is we might want to know what are the bounds. So this polyhedron fits inside a box in terms of x, y, and z. And so what region bounds does is it tells you what's the minimum x and the maximum x that this polyhedron lies in, or this object, whatever region it is, lies in. And then what are the minimum x, minimum y value, and the maximum y value. And then what's the minimum z value and what's the maximum z value. And so if we take these max values minus the min values, we can see that this snub cube lies in a box that's size 2.29 units wide, deep and high. We can also ask what is the center of the region, and so this is the center of mass, and it's called the region centroid. And when you just ask for the region centroid, it tells you what's the centroid of this region. Now I've used here the command chop to get rid of these rounding errors. And so you can really see that the center of this snub cube is 0, 0, 0. All right, so now let's modify these regions. We'll modify them so that we can build them together. So the way to change the size of a model is to use region resize. If you use only one parameter, then what we're going to get is we're going to get this object, and it's going to be that width. The x coordinate is going to be that size. So if we look at the region bounds, now the size of this object is 100 by 100 by 100. What we could do is if we put in not just one number, but we put in 3 numbers, then what that does is it skews the x value to be size 10, the y value to be size 1, so the y value to be size 1, and the z value to be size 2. Right, and so here's this is a skewed version of the snub cube, and you can see that it does indeed have those sizes. So this is going to be a very important thing to do at the end of your project, because when you're working in the computer, you're often working here and you're thinking, oh, I've got my object, and you're using the dimensions that make sense. Basically, these are units. As mathematicians, we often think about things in terms of units and not really in terms of inches, feet, miles, meters, centimeters, millimeters. We're not thinking in terms of a unit in our dimensions. But when you want to print things out, you're going to need to scale your model to be in millimeters. So this model here that we said was 100 units wide is going to be 100 millimeters wide, which is 10 centimeters, which is about 4 inches. So once you've got your model all set up and you've exported and you've re-imported it and it's the right size, or it's the right shape, then you'll probably want to use region resize to make sure that it's not just the right shape, but also the right size when you're 3D printing. And the size in 3D printing is a big deal. If you change the dimensions by a factor of 2, right, if you make it a bit 2 times bigger, what you're really doing is you're scaling the volume by a factor of 8. And so it basically becomes 8 times the cost to print something that's twice as wide as it was before. So some other things that you can do with your transformations is that you can we're going to take this cube and we're going to say, well, let's say we wanted to rotate this cube. So if we want to rotate the cube by a given angle, then so we want to take the green cube and make it the red cube. Well, how does rotating work? The way rotating works is, so we have in 3 dimensions, we have this object and we're rotating it, we're spinning it around an axis. So what we need to do is we need to specify what's this axis of rotation, how much are we spinning it around that axis of rotation, and then also where does this axis go through? Because spinning your object over here, so if your object's here and we're spinning about an axis over here, that's going to spin it far away. Whereas if we spin it about the center of the object, it's just going to spin in place. So we need to specify the angle that we're spinning it, the axis of rotation, so where is the direction of that line, what direction is that line going, and where does that line pass through. So in this example, I've chosen this green cube to spin by an angle of pi/4, and I'm spinning it in the xy plane. So what does that mean? It means that the axis of rotation is the z-axis. So that's the 0, 0, 1. And I wanted to spin it about its center. So to spin it about its center, well, the center of this is 1/2 in the x direction, 1/2 in the y direction. And the z doesn't really matter at this point, but we could have chosen 1/2, 1/2, 1/2 as well. And if we change the axis of rotation, that's going to then change the red cube. It's going to change what the red cube does. So if we did it only in the y direction, then here's a spin in the y direction with an axis of rotation in the y direction, and here's a spin with an axis of rotation in the x direction. All right, let's go back to where we were. That didn't work. You need to have some axis there. Okay, so that's rotating an object. We can also translate an object. All right, so in both of these examples, what we're doing, so this construction feels a little bit weird the first, second, third, 10th, 100th time you do it. But basically what we're doing is we're taking the cube and we're applying a transformation to it. So this rotated is going to be a new region that's going to transform this region by this rotation. Similarly, we're going to translate a cube by a certain distance. So here if we start with our green cube and we move towards the red cube, well, that's moving this in the direction 1 unit in the x direction, 1 unit in the y direction, and that gets us here. So we create a transformed region. We transforming the cube by a translation. So the thing that I like to use translation transform for, that I find very useful, is to create a region that's centered at the origin. Okay, so, oops. So here's what I'm going to do. Let's look at importing the shape of Germany into the computer. So how do you do that? We have country data. We're using country data. We're importing the shape of Germany. And I've used boundary discretized graphics to just give us the boundary representation of Germany. If you look at this, I've also put on the axes here. You can see this image is about it's 0.14 units tall, and it's not centered in the centroid of Germany. So what we want to do is we want to take this object, we want to change its size so that it's big enough, or maybe 2 inches across, and we also want it to be centered at the origin. So what does that mean we want to do? We want to figure out what the centroid of this current shape is, translate from 0, 0 to that point, so that's using a negative of the centroid for that. Right, so we're transforming Germany by translating it by this distance, and then we're resizing it because we want it to be 2 inches across. An inch is 2.54 centimeters. So when we resize the region and we transform it so that the center is now at the centroid of the object, then now this matches with what our real goal was in terms of having Germany here. All right, one last bit, and that has to do with some Boolean operations. So region intersection, region union, and region difference can be used to intersect, merge, or subtract two regions. They work well in 2 dimensions, but region intersection and region difference don't work well in 3 dimensions. In version 12.1 of Mathematica, when you have a boundary representation, they often work. Not always, but it still has problems with cell representations. All right, let me explain what I mean here. So here I have 3 different shapes: the oval, the triangle, and the square. So let's say we wanted to create an object that had the shape of the oval union with the shape of the triangle. When we do that, we can use region union. It takes the shape of the oval and the shape of the triangle and it puts them together. All right, what about the intersection? So now the intersection are all points that are in both the oval and the triangle, which is a shape that looks like this. Right, this is this shape in the overlap. And then we can talk about a region difference, which is, let's say we take the oval and we subtract off this little red square. That's going to give us the oval minus the square. All right, and so we can do that with boundary meshes as well. So here's my 3 shapes. I've got a tetrahedron, I've got a cube, and I've got a sphere. If I take the union of the sphere and the cube, you get this. If I take the union of the tetrahedron and the cube, I get this. If I take the intersection, what points are in both the sphere and the cube, you get this little quadrant or octant part of the sphere. Or we can say what is in the sphere but not in the cube. Right? That's kind of like what's left when you take out this bit here. And then we can say, well, what's in the tetrahedron but not in the cube? So this is the region difference between the tetrahedron and the cube. If you tried to do this with region meshes, so the cell representations of these objects, then the unions are fine. The unions work. But if you try to do region intersections, you can't find the intersection of those regions. You can't find the difference of these 2 regions. This one did actually work to give the region difference between the tetrahedron and the cube, but you can't bank on it. It won't always work. I think they're probably working on that as we speak. All right, that's it for today. Thanks. Take care.